One thing we often have to do is turn polar coordinates into rectangular coordinates because a lot of things can't graph anything in polar mode. So spreadsheets in particular, we need to be able to turn things into rectangular coordinates like traditional x and y. So if I gave you an r comma theta point, how could you turn it into an x and y? Think about that for a sec. One thing we can do is think about a right triangle approach like this. Put a right angle there. Does that help you figure out if you know what theta is, how high is that part, how long is that part, which one is, there should be a sine and a cosine, right? You might remember the expression SOHCAHTOA, which means sine is opposite over adjacent, hypotenuse. That's the S, the O, and the H. So that's saying that sine theta is the opposite part of that angle, so the side opposite of that angle, so that's the y value, divided by the hypotenuse, which has a length of r here. So we can say, well, if I just want y and I know theta and r, we can say y equals r times sine theta. What would you do to get the x value? Same basic thing, but with cosine. R times cosine theta. Do you notice anything about that? We're determining x and y based on some theta thing. That's basically a parametric equation, right? Like earlier in chapter 9, except now we have theta instead of t. Back in parametric equation territory, we said t is often time, but not always. And here it's not time, unless you're thinking of sweeping out a constant theta, like a constant amount of new theta per unit time. So that's turning polar coordinates into x and y, and it's reasonably straightforward. How about going the other way? What if I have some point x comma y? What is its polar form? The radius you can probably get without too much trouble. You again imagine a right angle triangle there, and the radius you can just get from the Pythagorean theorem. It's square root of x squared plus y squared, like that. The angle is trickier. Well, let's take the TOA. That says that tangent is equal to opposite over adjacent. But and here we know the opposite and adjacent, but we don't know tangent. So we're saying tangent theta is equal to the opposite angle, which is y, divided by opposite side divided by the the adjacent side, x. And we know x and y, but we don't know theta. We want to know just theta itself. So what we do is take the inverse tangent. So we could say that theta equals tangent inverse y over x, or sometimes we write it as arctangent y over x. I actually like arctangent as a better notation, because remember, this -1 doesn't mean raise it to the -1 power. It means the inverse function. So this is not a bad way to go. Do you see any potential trouble with this? Any particular values of y and x that could cause trouble spots? Well, if x is 0, that would be right up here on the axis, y being not 0, x being 0. We're going to get it divided by 0. That's trouble. So we would like to have a way to do things without getting divided by 0, and just in case x does happen to be 0. Any other trouble spots? Take some thinking. What if, so here's one trouble spot. What if my point is somewhere over here in the third quadrant, then x and y are negative. So x is less than 0, y is less than 0. What is y over x? Both are negative, so you're going to get a positive number. And here, y and x are both positive, and you get a positive number. So if you do y over x, you're losing the information about where x and y both positive, first quadrant, or where x and y both negative, third quadrant. And so your arctangent will only tell you stuff in the first quadrant here. It will never tell you that the angle is in the third quadrant. So that's a problem, right? So fortunately, there's a way around it that solves both problems at the same time. There's a function that's common in computer programming, for some reason not so common in math, called arctan2 or atan2. It's 2 like the sequel, or even better, like version 2.0. And instead of giving it y over x, you give it y and x separately. So you might give it x comma y, or in some other languages, it's arctan2 y comma x. I think one is in Excel, the other one's in Python. So the lesson is you got to check the documentation for the computer language you're working with. So let's go try that in Excel, because all this, you need to do stuff in Excel because it can't do polar coordinates. All right, here we are. I've got a bunch of thetas laid out. Let's do r equals 1 minus 0.9 times cosine, let's do sine theta. We did that before, so we're going to do 1 minus 0.9 times sine theta. One interesting thing, when we're doing radians, we often want theta to be multiples of pi, like pi over 4, pi over 3, pi over 2, pi over 6. But that's actually kind of a pain to do in Excel. It's easier to just use plain decimal values for theta. We won't get smack dab at values on the y-axis or x-axis other than at 0, but that's okay. If you really need to do it, send me an email and I'll help you. So we're just computing the r values here. But if I plot these two things, let's highlight that. I get basically a sine wave that's shifted up a little bit and flipped over and the amplitude's changed, but that's not what I want. This is just a Cartesian graph of like an independent variable like x versus a shifted sine wave. So I don't want that. I have to do, what's my x and y? So think about what formula I need to type here. Pause the video, maybe write it down for yourself, and then check against what I'm going to actually write. So remember, it's r times what? Well, I can't type an r like that. I have to say which cell. R times cosine theta and r times sine theta. And then I'll fill those down. And now, here's the trick. What do I want to plot? I want to plot just the x's and y's. So I'm going to highlight all those. And we got the cardioid we'd gotten before. Let me move on up. Put that there. So that worked at least. It's interesting here. We can see we're doing constant size steps in theta. Remember, theta is starting at 0, pointing along the positive x-axis and sweeping around. And the dots show us where each particular data point is. And they seem to be more closely spaced around here than they are around there. So it's kind of interesting and relates to something we'll do with arc length later. Now let's try practicing putting these rectangular coordinates back into polar form. Not that we really need to, but it's just good practice. We'll do theta and r. So what was the formula for theta as a function of x and y? Do you remember? It was atan2. And Excel, it prompts you, it says x number and then y number, so I don't even have to go look it up in the official help file. So x number and y number. And then r was the square root of x squared plus y squared. And we'll fill that down. And let's take a look. Am I getting the same thing here as I had there? Yep. How about here? Yep, that's good. Let's look at some points in the third quadrant because we knew we would have some trouble when both x and y were negative if I was using arctan 1 where you divide x by y. So here's a point where both x and y are negative, and am I getting, let's see, so this is the arctan negative 2.7, that's interesting, and then a radius of 1.31. Well, the radius is matching, but I'm not getting the same number for theta here and arctan here. Can you think of what the difference might be? In particular, this is negative, so it's almost like instead of going all the way around to the third quadrant, it's going backwards from 0. And that means that this number and this number should be different by how much? Basically a full turn. So what if we subtract one from the other? Let's try this. Add 2 pi to the arctan 2 value. So we'll say here's my arctan 2 value plus 2 times pi. And we do in fact get the radian measure we got there. So this is not something you have to do in any of the homework, but it's, toward understanding what's going on. Apparently arctan 2 doesn't give us values from 0 to 2 pi. It gives us values probably from positive pi and then all the way back through negative pi.